Okay, so I'm appropriately attired. I've got my lab coat on, it's buttoned. I don't have a long hair, I'm not a bloody hippie. But if I did, it would be tucked away. I put my safety glasses on immediately as I walked in. If I didn't, and you get about this far, you're gonna get poked in the eye. Right? That way you will remember, but more importantly, you'll keep your eyesight. Safety is critical in the industry, energy industry. You're in a dangerous environment. If you're in a lab, we are operating in extra sensitive lab safety mode, regardless of what's going on. You need to be cognitive of the risks. So I'm going to go quickly over the proximate first and then the ultimate analysis. So our instrumentation is over here. This is a LECO TGA 701. That's the kind of information that you need to put into the method section, right? The way we're doing the proximate analysis is by difference in mass. This is essentially a glorified oven. If you take a peer in, you can see we have a carousel. There is a balance here. This particular crucible is nice and clean. Is a reference crucible. We don't put sample in there, but you can see that we have multiple locations that we can have 20 or so samples for the proximate analysis. The sample sits in a crucible, and that's the correct terminology to use. They also have a close-fitting cover. Again, that is the correct terminology to use. You gain credibility by using the lexicon of the industry. So you go in and say the coal was, was placed in a cup with a lid, then we're going to understand that you're not at the technical level that we would expect. So, crucible, tight-fitting cover. The instrument is loaded with clean crucibles, and it goes around and labels what determines the empty mass of each of the crucibles. Once that occurs, we take them out and we use tongs to make that easier. And obviously when it gets hot, we need to use these tongs to ensure we don't get burned. We have a microbalance sitting around the corner or here. We're going to put in approximately 1 gram of sample, but we're going to have it accurately weighed. Our balance that is used here to actually weigh the material actual weight is both a high accuracy and a high precision. It's going to go to 4 decimal places. We don't need that precision here because we're just sort of loading in approximately 1 gram, but here the instrument needs that level of precision. Precision relates to the decimal places and the uncertainty in the data. The accuracy relates to whether that data is right. Because coal is highly variable, we're going to do at least triplicate analysis for all of these components. And I don't want to see all that data. I want to see means and standard deviations. It's important that you include uncertainty in your data. Again, that's how engineers lose instant credibility by not doing what they're supposed to do, present the data in a manner which makes the interpretation easy. So if you're doing dumps of data, you're essentially saying you can go work it out for yourself, I'm off to the pub. You need to provide that takeaway message and the data that backs it up in the appropriate format. So with uncertainty, so means and standard deviations are expected. So samples are placed in, the carousel goes around, it gets weighed, and then it goes through the moisture determining step. This is essentially a glorified oven with a balancing instrument. There are specific heating rates as in the ASTM. And it's going to periodically go up to about 110 degrees Celsius, but read the STM for the actual numbers. And it's going to weigh them periodically. When it's gone through and weighed them, they all have got to the point where there is no significant change, that is going to be considered as the moisture value. During this time, it's an inert atmosphere. We have nitrogen gas flowing through, and again, read the STM, you'll say that it has to exchange the volumes a certain number of times per minute. After the moisture step has been recorded, the lid opens and we place the cover on the crucible. It goes around again and reweighs the new mass. so we know what the weight of the cover is. And then the process goes into its volatile matter stage. During this stage, it's going to heat up to 950 degrees Celsius. Again, read the ASTM to make sure that's the correct value. It's going to stay in an inert atmosphere. There is going to be mass loss. The reason for the cover is to prevent coals from sparking or jetting out because of that mass loss, or fracturing and sending fragments out. In the case of bituminous coals, they will, even though a small amount of material is going to be in here, it will fill the crucible when it thermally expands and forms a foam, a coke, which we call a coke button, and some of them can actually raise the lid several centimeters above the cover, several centimeters above the crucible. So it helps keep it in and prevents it from overflowing. After 7 minutes of being at that temperature, there's going to be no weight loss, and the oven's going to cool down. We're going to need it to cool down so there's no thermal shock to the system. And you'll notice I'm calling it an instrument and not a machine. Instrument has implications of a higher level of precision and maybe greater complexity. So once the instrument is cooled down to an acceptable temperature, the lid opens, the cover removed. And again, they're going to be hot, so we will be using our tongs, and we have safety gloves as well. And it goes through the process of heating the oven up again to the temperature used for the oxidation, that's the burn off, to generate the ash yield. Again, don't use ash content, you can use ash yield, or there's no ash in coal essentially as far as you're concerned, or you can just use ash. There's not the ash content. Significance being that there's a mass gain or mass loss as the mineral matter transforms into ash in an oxidative environment. So moisture is done in nitrogen, volatile matter is done in nitrogen. When it reaches the appropriate temperature for that burn-off stage, where we're removing that fixed carbon, it's an oxygen atmosphere. So we determine moisture, volatile matter, ash yield, fixed carbon is by difference. Oven cools down, samples are taken out, we reweigh new crucibles, and we go through the process again. When we give you the data, we're going to give you the data typically in the format of here's the initial crucible weight, here's the mass after the weight loss, the difference is going to be the moisture. So make sure you understand the format in which we're giving you the data. Obviously there's manipulations you need to do. When you do those manipulations, you need to tell me on what basis is the data. Is it being presented as received? Is it being presented dry? Is it being presented dry ash free? Is it being presented dry mineral matter free? Approximate data, ultimate data, all need to have that component. So very brief going over what it's done. Read the ASTMs, you can extract the useful information from that. The theory is how this instrument works. There's no discussion of any of the samples that we utilize in here. It's generic. You can say coal, but I don't need to know anything about the samples because that goes into the methods section. Do not confuse theory and methods. Theory is how does the instrument function, temperatures, durations, atmospheres, things along those lines, and then mathematical manipulations. Methods is enough information that somebody can come and repeat the analysis. So what instrument, what ASTM, what sample, how many runs, what corrections and manipulations. So, moving on. This is the LECO TrueSpec CHN analyzer. We also have a sulfur component added in. I'll start with the sulfur as it's the easier one to do. This has a horizontal furnace. So you can see the furnace here. There are some particulate filter traps and some things to absorb moisture so those don't go into the infrared detector. We load our ceramic boat, and again, that is the correct term. I have a balance over here. It's a high precision, highly accurate balance. It goes to 5 decimal places, but the ASTM says we utilize 4. So when I push a button on the balance, it tells the computer this is the date and mass of the sample. Once we've done conditioning runs, the conditioning runs here are, I run it a couple of times where I don't actually put the sample in. it gets the furnace at the right temperature, it gets the infrared sensor warmed up, and we sweep any sort of contaminants out of the system. This doesn't take much to do that. It's on all the time, 24 hours a day when it's working. Right now it's cold, and so it's just a small tweak in temperature. It's operated, I think, at 1,350 degrees Celsius. Again, you should check that at the ASTM. So once the computer tells me it's okay to add the sample, we will slide the door open. If it was on, it would be so bright I can't look into it. And so we have a shield here that's going to help me push this boat in. And so as the ceramic boat goes into the furnace, I would look to see how far it's going. I would close the door. The gases are collected, sent over to the other instruments where infrared analysis will do an integration over the time period of the emissions to work out how much sulfur dioxide is in there. There is an oxygen lance that sits right above where that ceramic boat is sitting, and so that's where the oxygen is coming in. We do vary the flow rates and doing other things that are a bit of a detail to work that out. When it's ready, I'd be able to use this again to go in. You need to be careful not to hit the ceramic oxygen lance because it's very very brittle, and this would come out glowing red hot. So that's why this shelf exists. And this is why we don't have long hair, because if you were a hippie, young lady with long hair, and you turned around like this, your hair is sitting on a glowing red hot ceramic boat, and I would be frantically pounding your head trying to put the flames out. Or if you were not a good student, I'd be throwing you out into the car park, so we have one less report to grade. So safety is paramount in these systems. I always tell you to wash your hands after the lab. We use catalysts sometimes in this space when we look to see what the risks of or health implications of contamination with these catalysts. They are quite significant, and so you need to wash your hands when you leave. This is why there's no gum chewing, so I don't want you being poisoned unless I've done it deliberately. So no food and drink in the lab for these reasons. So very simple, separate ASTM for that. Easy to do, simple conditioning runs, analysis and corrections. Sulfur is made a little bit more difficult because there's both organic and inorganic contributions. All right, so the CHN. What we have here is a primary furnace and a secondary furnace. We put samples into this auto feeder. Again, we can't just do one sample. We're going to do at least triplicate analysis, probably more. And so we have samples that will fit into an aluminium ball that will sit in here. This system rotates, and as it rotates, the sample will drop into this loading mechanism that is brought over into a shelf above the furnace. We do need, before we start, to do a whole bunch of conditioning runs. We do a system check, says the infrared sensors are up to temperature, as well as the thermal conductivity apparatus is working. It flushes the system with helium to get rid of background air contamination. But it's not enough when we start up to immediately start running. So what we have to do is a whole bunch of conditioning runs. They're sometimes called blanks. We don't treat them as blanks because we aren't going to take that data away from the results we get. So what happens is I'll find a high nitrogen signal that's been sitting over the weekend because air has infiltrated the system. So the purge process will take helium through the system. It says it goes through the process of doing an analysis. It's just that there's no actual sample added into the instrument. So through about 5 conditioning runs, again to the point where I get reasonable background level of nitrogen, so very low contributions. So again, balance a foil sample holder. If I was doing this for real, I would be wearing gloves because I wouldn't want my oils to contaminate the data. It would sit in this balance, which is again high precision, high accuracy, 5 decimal places. We would weigh to 4 decimal places, push a button, it gets transferred to the computer. We know the mass of the material. We need to know the proximate analysis because this isn't all organic material. It's contaminated by moisture. Maybe contamination is the wrong word because in coal it's part of the structure perhaps for some ranks, but it has a moisture contribution that's going to artificially boost our hydrogen value. But we also have inorganics which are going to again artificially boost all the data or reduce all the data because I'm not just looking at the coal organic material, I've also got the inorganics. So I need to know what those data is from the proximate analysis so it can be corrected. So the sample is placed in here, scrunched up so it fits in the auto feeder goes along, we've done conditioning runs, the sample is sitting on a shelf. When the system is ready, the shelf is retracted, we use compressed air to do these movements. Sample falls down to the primary furnace, there is a combustion in ultra pure oxygen. Again, read the ASTM for these sorts of details and what the temperature, allowable temperature range should be. You also might want to look at LECO company and put the specifications in. Again, LECO True Specs THN, that's the kind of information that I need to know for the methods. I don't need to know it for the theory. It's generic, but each installation is a little bit different, so I don't need to know the samples used in the theory, I need to know how the equipment functions. So, sample in a furnace, I believe the temperature is 950 degrees Celsius. Again, look it up. After that, the gases go through an afterburner furnace, probably around 800 degrees Celsius for this particular instrumentation. But that's going to ensure that there is complete combustion. The gases are then collected internally in what's known as a ballast. It's the size of a coffee can. The gases coming off initially are going to be different than the gases coming off at the end. The volatiles are different from the combustion products in the chart. And so you can't just do analysis right away. You've got to collect all of that data. A small portion of that, after things have reached equilibrium, we've gone through the oxygen feeding system, maybe multiple different flow rates, again, the detail perhaps. The gases are at equilibrium. A very small portion, 3 cubic centimeters in this case, will go off to the infrared sensors. We have separate ones for both carbon dioxide and water. And from those, we use calibrations to know what those values are. Again, the water data needs to be corrected because we have moisture in the sample. It's very high in biomass, so it's not dry. So these are significant corrections to make, particularly as well at low rank coal, where moisture can be quite high. After that is done, the other portion of the gas is sent through a third furnace. This one is full of copper turnings, I forget the temperature, but it's going to strip out the oxygen and convert our NOx to nitrogen gas. That nitrogen gas is going to go through a thermal conductivity conductor, and we know the thermal conductivity of helium, and we can work out what the concentration is from that change in thermal conductivity when nitrogen gas is present. Only one of the NOx gases is infrared active, and so we can't use NOx for that case. So, how do we calibrate the instrument? We purchase standards. A calibration might be 5 to 10 samples, probably done in at least triplicate, maybe even more. And so you're starting to look at 30 analyses, maybe 40 analyses. So we don't do the calibration very often. We have a calibration for high rank coals, we have a calibration for low rank coals, for biomass. We have some calibrations that will span that rank range, so we can do maybe things added in together. And it's important that we get that right. So there's calibrations, we do it for the carbon, the nitrogen, the sulfur, the hydrogen. Our oxygen we determine by difference. Over time, the instrument, however, is going to start giving you different values for the same sample. This is known as drift. To compensate for drift, every 10th, 12th sample, depending on how frequently you're doing things, should be the same sample. So if I know that my coal is 80.2 weight % carbon on a dry basis, and I keep looking at that data and I see it starts changing to 80.1, 80.0, I can say there is a drift in the instrument. You make a move to the calibration line, it corrects that data, and it's a weighted move, and it will go back and correct all of the other information. So it's quite a nice system, but we do have to be careful of that drift. So just to sort of go through the system again, you have calibration runs, the system purges, it goes through a combustion step, there's an analysis step, and then of course we have to accommodate drift, and then of course there are corrections to the data and manipulations that are well covered in the ASTMs. Don't think that I need to add any additional information on this. Read the technical documents, read the information on how the data is used. This is certainly a case where this data and the calorific value are used in combination. So keep in mind we'll be doing a calorific value determination as well, and you need to know that information. All right, that's all.